Welcome to section 20.1, part 1. This is the 198th session of the CISSP exam prep series. In this session, we'll look at where security fits into custom software. We'll answer several questions. Why do homegrown applications carry so much risk? What kinds of programming languages exist? And why does that matter? How does compiled code differ from interpreted code in a security sense? What danger hides inside shared libraries and machine learning components? What tools do developers rely on? And how does object-oriented design shape security? And what does assurance really buy you? Why does this matter beyond the exam? Because you will sit in design meetings where developers make choices that quietly set the security posture for years. Picture a logistics firm writing its own route planning app. If a careless engineer leaves a backdoor or a sloppy input path, that flaw ships to every warehouse. Knowing how software is built lets you spot these risks before they harden into production. So, why do custom-built applications carry so much risk? Because organizations write their own software to serve goals, no vendor product covers, and that code is only as safe as the people who write it. A rushed or malicious developer can plant a hidden backdoor, leave a buffer overflow, or forget a check that lets an outsider in. The fix is to weave security controls through the entire development lifecycle rather than bolting them on later. Think of building a house. Wiring and plumbing are far cheaper to route correctly while the walls are open than to tear open finished drywall afterward. Why build security in from the very first stage? Because retrofitting protection into a finished system is slow, costly, and leaky. Every application deserves security proportional to how sensitive its data is and how critical its job is. A payroll engine handling salaries needs far tighter guarding than an internal lunch menu page. Decide the security posture while the design is still fluid, and the whole structure bends to accommodate it. What kinds of programming languages do developers actually use? At the bottom sits machine language. The raw ones and zeros a specific processor understands, which almost no human reads directly. One step up is assembly language, which swaps those numbers for short mnemonics, but still demands deep hardware knowledge and endless lines for simple tasks. Above that live high-level languages like Python, Java, and C#, which read closer to human instructions, speed up development, and travel more easily across platforms. Think of it as the difference between speaking in Morse code, in shorthand abbreviations, or in plain sentences. How does a program actually get from source code to running software? Two paths exist: compilation and interpretation. A compiled language uses a compiler to translate the human-readable source into an executable file built for one operating system, and that finished file is what you hand to users. Normally, nobody can read the original instructions inside it, but reverse engineering specialists use decompilers and disassemblers to work backward towards source or assembly, which is handy for malware analysis. Obfuscation deliberately scrambles an executable to slow those tools down. Some languages instead lean on a runtime, like the Java virtual machine, that users install so the same compiled code runs anywhere. How does interpreted code differ? And what does that mean for security? With an interpreted language such as Python or JavaScript, you ship the source code itself, and an interpreter on the user's machine runs it line by line. Because the source travels in the open, anyone can read it. That cuts both ways. Compiled code resists outside tampering, but a dishonest developer can bury a backdoor no end user will ever see. Interpreted code exposes that hidden logic to inspection, yet everyone who touches the file can also alter it. Picture a sealed appliance versus a recipe card. One hides its inner workings, the other invites both review and meddling. Why are shared libraries both a gift and a hazard? Developers reuse pre-written libraries so they never rebuild common functions like sorting or text handling from scratch, which saves enormous effort. The catch is that a flaw in a popular library spreads to everything that includes it, often silently. A famous flaw in a widely used encryption library forced administrators across the globe to scramble because countless products had bundled it without users realizing. So track where your borrowed code comes from and watch for newly disclosed weaknesses in it. The same discipline now extends to machine learning, where pulling a pre-trained model or dataset from an untrusted source can smuggle in hidden backdoors or poison behavior. What tools and design styles shape how developers work? The central tool is the integrated development environment, a single workspace where a programmer writes, tests, debugs, and compiles code together. On the design side, object-oriented programming models a system as a collection of objects that pass messages and perform actions. A banking program, for instance, might have objects for accounts, account holders, and employees, each carrying methods like adding funds or closing an account. Objects can inherit behavior from a parent class, so a checking object gains everything an account has plus its own extras. From a security angle, this gives you a black box style of abstraction. Each object is encapsulated and self-contained, reachable only through defined messages, so a user works the interface without touching the fragile internals. What do the core object-oriented terms mean in practice? A message is the input sent to an object, and a method is the internal code that runs in response. The observable result is the behavior. A class is the shared blueprint of methods, and each object is an instance built from that blueprint. Inheritance passes methods from a parent class down to a child, while delegation hands off a request an object cannot handle itself. Polymorphism lets one object answer the same message differently as conditions change. Two quality measures round it out. High cohesion means a class's methods share a clear common purpose, which is good design. Low coupling means objects depend little on each other, which makes them easier to fix and update. What does assurance actually give you? Assurance is the formalized process of building trust into a system's whole life cycle, confirming that the security mechanisms you designed keep enforcing the policy over time. It is not a single test, but an ongoing confidence that the controls do what they claim. In government settings, a standardized approach called the Common Criteria provides a shared yardstick for measuring that trust. Think of it as an inspection regime, not a one-time stamp that keeps vouching for the system as it ages. So let's bring it together. Custom software carries real risk, so you build security in from the first design stage rather than patching it on later. Languages range from raw machine code up to high-level tongues, and the compile or interpret choice trades tamper resistance against transparency. Shared libraries and machine learning components inherit any hidden flaws, so you vet their origins. Integrated environments and object-oriented design shape both productivity and protection, and assurance keeps confirming the controls hold over the system's life. Master these foundations, and the rest of the development story fits neatly on top. The MCQs covering all the topics and concepts from this session are available on rucloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.